All right, okay, let's get started. Let me just very quickly go over some logistics. Okay, so there is no homework due next week, but starting from next week, we'll have weekly homeworks, and they're going to be due on Wednesday, okay, just before class. All right, and so we are going to first discuss aerodynamics fundamentals and incompressible potential flow. Afterwards, we have our first quiz. It's going to be an in-class quiz on a little bit more than a month from now. All right, so that's our first quiz. The second quiz, again, is going to be in class, and it's about 1 month after that. So after both quizzes, we'll get into projects, and in the very end, the final project report is going to be due also in class on December 11th. All right, so that's going to be the last lecture. Actually, you'll be presenting your project on that day. So yeah, so these are the most important dates. I just want you to know, like very early in the semester. And if you go to Canvas, there should be a link to this notebook, right? You should all be able to access that, right? Yeah. Okay. So that's here. Okay. Any questions? All right. Okay. So last lecture we ended with watching this video. I just want you to redo it a little bit, just the important parts. And we were focused on saying that what is providing the turning forces are actually the lift force, right? Because we are banking, the lift force is pointing not just upward towards the direction orthogonal to the wings. And then we get to this point where we are visualizing. If you visualize a column of air, a cylindrical column of air, the column that the airplane passes was disturbed. It is disturbed from being completely still to moving downwards, right? At a fraction of the speed of the airplane. And that's what the downward moving air is, what is kind of creating the disturbance on the sand, because the air moves down, impacts the sand. All right. And particularly, we were watching when the pilot pulls up.
Pumping 3, 2, 1.
Because the lift suddenly increases by a lot. The exchange of momentum, right? The lift is basically the force from the air to the airplane points upward. The force from the airplane to the air is pointing downwards. So because the lift increases, there is more force on the air, and the air has to move. If it's the same cylinder, the air has to move down at a faster speed, right? So if the pilot is pulling 8G, for example, the air has to move downward at 8 times the speed. That's why now the air actually kicks the sand up instead of just looking like a trail. Okay, so this is the model we'll be thinking. And today we are going to be following on what we did on the last lecture, and we are going to be answering a series of questions. So we are assuming the passage of the airplane sets in motion a cylinder of air, the diameter of which is the span of the wing, and we use B for the span of the wing. And we use rho as the density of air, and the speed of the airplane is V. So we'll start answering these questions very similar to the Jesus Christ the Lizard, right, that we watched on Wednesday. But today is real aerodynamics. Okay, so instead of thinking about discrete balls of water moving down, now you are thinking about a continuous column of air being disturbed. So please, again, come over, form groups of 2 people, and I'll get more chalks. I ordered some color chalks for you if you prefer, but not this lecture. So please form groups of 2 and start answering these questions. And these questions are going to be very similar to last lecture. I hope everybody is able to answer them, but there are going to be more questions after you finish answering these set of questions. So please get ready for more difficult stuff later on. Let me move this a little bit away so you can come over.
Cylinder.
Yeah, it's like behind the.
You
it's like
just
the shoulder,
outline.
follows the shoulder.
By the way, the column is horizontal, right? So it's not
like going up.
It's not going up, right? It's following, it's trailing this airplane.
Oh, okay.
Yeah, the column is not vertical; it's horizontal. Right? So basically, it's a column trailing this airplane.
Like meters per second. For 1 second.
Yeah, that's the correct answer for the first question.
Just lift off. So yeah. How much?
Yeah, see, most people get the first question. So to go to the second question, think about what we did on Wednesday, right? We have to relate mass with momentum, and then momentum with force. All right.
Oh, yeah. Oh, wait, yes. Going.
So you're done. There's no question. Okay, you're also, yeah, very good, very good. So just get ready for the next set of questions if you are done. Yeah, this is momentum per second, which I'm describing, right? So that's actually lift. Yeah. Okay. So if everybody has derived the momentum per second, that's actually the same as lift.
Demonstrate that second equals lift.
Yeah, very good. Again, like for those people who got the answer, you're gonna see like your answer has rho v squared in it, right? And why is there rho v squared? Because rho is proportional to how much mass you are disturbing, right? For the same geometry of air being disturbed, the higher density is, the more mass you're disturbing. And there are v squared, v times v. The two v's comes from two different places. One of these v's comes from momentum, right? The momentum is proportional to how fast you're disturbing the air. And we are assuming the speed the air is moving downward is proportional to the speed of the airplane, right? That's why there is one v. The other v is how much air you're disturbing per second. The faster you're traveling, the more air you're disturbing, right, over each second. That's why there is a v squared. I mean, that's actually why all aerodynamic forces, or hydrodynamic forces, if you wish, is proportional to rho v squared. All right. Okay, so good. So then we are able to use this to answer some questions. Let's get to the next, more difficult set of questions. Any questions regarding to these answers? So let me just write it down. So the first answer is going to be rho, the mass of air per second, let's say m dot, is going to be rho times pi b squared over 4, right? You all got this, right? And the lift force is simply m dot times xv, right? Which when you plug in is equal to rho No, this is times v, right? M dot. So this is a volume, and then like you have a rho times v squared times b squared, and pi over 4, right? You all got the same answer here?
With X. Oh, yeah.
With x, yeah, times x. Thank you. Okay, now let's actually just copy these. Why don't I get a selection? Okay, and move to the next set of questions. So how much, now we think about kinetic energy. We have looked at momentum, right? Momentum conservation gives us the lift. Now think about energy conservation. How much kinetic energy is in the mass of air set in motion by the airplane in 1 second? All right. And considering conservation of energy, where do you think that energy comes from? Like you don't have to write down, but like get an answer, discuss among yourself and get an answer ready. Okay, and how much power is needed to feed this kinetic energy that is in the wake, like in that column of descending air? All right, again, express all of these using the same numbers. Okay, for the second question. Now the third question is, remember, like our lift formula has an x. Can you express the formula of power in terms of, not in terms of x, but now in terms of this lift? So these are 3 questions, right? In the second question, you can use x. In the third question, get rid of x and use the lift instead. All right, please.
So the first one's 1 second. Oh, what's wrong? Wait, I'm not sure if it's I'm not sure if it's because the potential power is completely.
So you get how much kinetic energy you have to feed it per second, right? That is power. All right. Yes. So this is the answer to these questions are the same, but like also you also want to figure out where does that energy come from.
I mean, yeah, like
Very good.
So
Like the airplane one, that's also going to give you like this
Yeah.
squared.
What should be the velocity?
Exactly, right? We are asking how much kinetic energy is
In a row.
Displacing it. So the air is
by the square of the velocity of the air. Square.
So that's other easy. Or actually, no, it is. Quantum.
Oh, this is math. Yeah.
Exactly. Because it's about changing the line pressure from put the switch in the table and
How does that translate into power?
So, yeah, all of our 1630s just suck. Really? Well, this is like this one's in class. That's what it said. The other ones are all small class. I think you aren't able to execute that. I'm pretty sure it's like 2 major cycles per major whatever.
From the 1970s.
You're thinking about how main turbo the first part, and they actually gel. And they supposedly activate it. I didn't get one. Dude, my TV. I'm just sitting there like, man. Dude, no. We're doing visualizing. Oh, wait. It's just like, do whatever you want to do. I don't care.
There's probably said something like in this class.
As long as you graduate.
I feel like probably more like fluids.
Yeah, they don't really.
I don't think it's nearly as bad as not like you guys are impossible, but it's easier.
Is Will not here?
Probably not even like. I don't think it's even the same context as 801. I feel like you kind of skip over some of the. They skip over some of the physics that's in like associated with like fluids or like.
Yeah, so express the same thing without having
Like can you draw it?
For a second, I thought that we would have. So this is a recitation. Does that mean we have a lecture?
What's your answer?
This was, where is it? So, and this was.
So does that remind you of anything you learned in Unified?
You have to like push down.
Honestly, no.
What is proportional to square of lift and inversely proportional to the square of span?
I can already feel that. It sounds like it's
Or what increases quadratically as you increase lift, but decrease quadratically as you increase span? Sorry, what is your?
I have no idea.
Oh, nice. Yeah. So.
What are the units of this?
Good. Very good.
good. I like that. Yeah. Algebra.
Meters per second squared.
Oh, so this is probably
Her problems like this are simultaneously hard.
right. Oh, and you have the same.
Yes.
Figure should be
Yes, this is correct.
kilograms per second squared.
Oh, but there is still X.
Right.
So this is relation between L and X. And just to divide everything.
Oh, yeah. No, kilogram meters per second squared.
learned lift is the momentum, force is like momentum, power is energy over energy over energy per time.
Because then you're squaring this as well.
Force is momentum per time.
Sorry, would you mind to leave some space for the other team? Yeah, that's very good. Yeah, if you're finished, there are no more questions. You can go back to your seat and just get ready to answer where the energy comes from, and also think about where you. Does this remind you of anything unified? That's the final answer. All right.
Was it wing loading? Dude, those. Is it wing bending?
No, but it's still a formula. Oh wait, reflection. No, we already could have got there.
I feel like that's the lift squared and then numerator like very.
Yeah, the L squared and then the rho.
Oh, very good. Yeah.
Power. Meters.
Yeah.
Oh yeah, because you move into it in the meters. Facts.
Oh wait, no.
Yeah.
Let's.
Kind of lost.
What's the code?
Very good. I think all the teams got it, right? Did you also get it?
What do we like? It's like how is C on L?
Oh, L is like 1/2 V infinity rho L CL. It's like. Yeah. All right.
That's actually such a good point. Because I was like, oh. Which I guess is like, oh, maybe it has to come through and just be like labeled.
Did you ask them? Or did you just call the other stuff? Oh, okay.
Yeah. So, yeah, because the 30%. Design project is 35%.
Something like that. It's probably more. Much more.
I'm glad the project is worth the work. Because I think that's
Just
capital control is great.
and it's already on 6.
Okay, good. Yeah, there is a factor of 2. Otherwise, it's all good. All right, I think all the teams gets it, and let me just write down the answer here. Okay, so the amount of kinetic energy is basically equal to half of m dot times the speed of the air, not epsilon, xv squared, right? Okay, so after you calculate this out is 1/8 of pi and b squared x squared v cubed. All right, okay, and this is the power. So because this is the amount of kinetic energy you put into the wake per second, it is exactly how much power you need to feed that kinetic energy, because power is actually the amount of energy increase or decrease per second, amount of energy transfer per second, right? Okay, and where does that kinetic energy come from? Like, again, think about this airplane. Yes?
The engine pushing down like the fuel.
The engine. Okay, very good. The engine is the source, but like it's actually not the engine pushing down, right? The engine is actually pushing the airplane forward. In reality, if there is no engine, right? If the engine is shut down, what do you think is going to happen to the airplane? if it keeps dumping energy into the wake? It'll fall, but like there is still lift, right? Yeah. It can go down and lose potential energy. Yeah, that's one way. It can use the potential energy to dump the energy into the wake. Another way, yes.
Like stall.
Yes, it may slow down, right? It may transfer its kinetic energy into the wake by slowing down. All right. Actually, the engine exactly counters that, right? The engine prevents the airplane from slowing down or prevents the airplane from slowly gliding downwards. So all of these answers are correct, right? Well, another way to say it is the engine counteracts with the drag, which would be on the airplane, would be slowing down the airplane if it does not, right, produce the thrust. Okay. So now can you express the formula in terms of lift? It's essentially just figure this x out, right? And well, one thing is that when you compare this formula with this formula, you can first write it as a half. Pi is in both. Sorry, I forget the rho. Rho is in m dot. So rho is in both. V squared is in both, except for there is another v here. And the x is in both, except for there is another x here. So this times lift is actually the formula, right? But again, we still have an x here. So we need to also divide by a bunch of other things that we can say, okay, x is equal to L divided by this bunch. So if you further divide it, you're going to get lift squared and half of rho v b squared times anything else times pi, right? Is that the formula everybody gets? I think so, right? Okay. Now the question is, does this remind you of anything? The coefficient of lift, which is CL, right? CL is going to be lift divided by half rho v squared, further divided by the area of the wing, right? So it's a little bit different from here. And let me do something maybe that can bring your memory even a little bit more. So let me divide this power by the velocity of the airplane. Okay. That is going to be L squared divided by a half of rho v squared b squared pi. Again, somebody said this power can be provided by the engine, right? So if the engine provides exactly that much power and assume the airplane doesn't really dump energy into anything else, then the airplane is going to be in steady state flight. It doesn't increase or decrease in altitude. It also doesn't slow down or accelerate. Then what is P over V? What is the engine power divided by velocity of the airplane? What is the formula for the output of the power output of an engine when it's creating thrust? When you're pushing an object with a speed of v, like with the force of F, like how much power are you exerting? Come on, physics 1, right? When you're pushing an object with the speed v, with the force F, how much power are you exerting? Are you giving the object?
It's that force times velocity.
Force times velocity is that power, right? So the power divided by velocity is
Force.
the thrust, right?
Oh.
It's the thrust required to counteract the drag, which means this is some kind of drag. Okay. Any light bulbs coming up? Anything you learned in Unified? Maybe when you learned in Unified, it's expressed in a different way. Maybe it's expressed in the coefficient of lift and coefficient of drag. Maybe that's why it doesn't really ring a bell here. But this is exactly the formula for induced drag. Okay. I mean, if the induced drag is proportional to the square of the lift, right? Inversely proportional to the aerodynamic pressure, half rho v squared, and inversely proportional to the square of the span. So I guess in Unified, did you learn it in the coefficient form, like CDI? Okay, yeah, if you express in the coefficient form, you're going to be dividing everything. Maybe let me write it out. If you learn it in the coefficient form, then you're going to be dividing both sides by what? So what is CD? CD is equal to D divided by half rho v square, and the area of the wing. Okay, and the area of the wing is do you know the areas of the wing is b squared divided by aspect ratio? Right, because b divided by aspect ratio is the chord length. Okay, so b times b over aspect ratio is the area of the wing. Okay, so that's CD, and CL is exactly the same. Lift divided by half rho v square, b squared divided by aspect ratio, and then if you divide both sides by the same thing, you're gonna see that CDI, the induced drag coefficient, is going to be okay, you have L squared, right? So let's divide one of these L by this. So you get CL times, okay, so get the CL and then L divided by what is already in the denominator, right? Is that right? So I have L squared in here. I'm dividing one of these L's by this bunch so that I get both CD and CL. The other L, I just keep it here and I keep everything in the denominator here. Okay, good. Okay, then we'll see how do we transform all these denominator into something that's the same as this bunch. The only thing we need to do is what? We need to change this pi to 1 over aspect ratio, right? Okay, so we can basically we can divide by aspect ratio both in the numerator and the denominator, and what we get is we still have the CL, and that becomes CL divided by aspect ratio, and in the underneath I just get pi, right? So essentially that is CL squared over pi aspect ratio. All right. So that's like probably what you learned in Unified. All right, good. Okay. Anyway, so this is the reason I'm discussing this is the following. Yeah. So this is basically the induced drag, and so the reason I'm discussing this is because now this entire course, aerodynamics, is about various aerodynamic models. Okay, so this is an example of an aerodynamic model. You're probably not going to find it in any textbook because I kind of came up with it. But it's not going to be a particularly insightful one. But it is already a model in the sense that, okay, so the model is the following. The passage of the airplane sets in motion a cylinder of air, the diameter of which is the span of the wing, right, moving in the opposite direction of the lift vector. If the lift vector points up, this cylinder is going to be moving down. it is useful in the sense that it explains the lift through conservation of momentum, right? Okay, now you can tell people like why there is lift, because the airplane kind of push the air downward and leaves a column of downward moving air afterwards. It also explains the induced drag through the conservation of energy, right? You know, like why there is induced drag, because it has to disturb the air, right? And in order to get lift, it has to move the air downwards. And once it moves the air downward, you have to spend energy, and that's where induced drag comes from. It can also quantitatively predict how much induced drag there is, right? And the formula we get is pretty much the same as we derived with an airplane-centric view. I don't know if you derived it in Unified or not, but like if you did, it's probably like an airplane-centric view, right? Looking at how the vertical structure of the wing actually affects the wing itself, tilts the lift vector and things like that. But it's actually also wrong, right? A model is necessarily a model. I mean, a model is not reality because it doesn't exactly coincide with reality. In this case, think about what's wrong with the model, right? First of all, unlike a solid object, a column of air cannot just move downward by itself, like in vacuum. The air outside of the cylinder has to make way for the cylinder, right? In the sense that the air below that cylinder, they have to go away. And the also air above the cylinder, they have to come to fill the space left by the downward moving cylinder. So there is air even outside of the cylinder that's moving. So for example, the kinetic energy formula we computed assumes that the only thing moving is the cylinder. So that's just not correct, right? There is more kinetic energy outside of the cylinder, okay? And also, as we are going to see, I'm pretty sure next week, the air inside of the cylinder is actually not going to be moving at a uniform speed. And exactly what is the distribution of air, of velocity inside this cylinder, right? Where does air move faster? Where does air move slower? What direction is the air moving? Actually depends on the span-wise loading of the airplane. Okay, so here I'm assuming a cylinder moving down uniformly is an okay approximation only for a well-designed airplane. Okay. And finally, that explanation is not really satisfactory. You can ask a lot about like why, right? Like why is the cylinder of air set in motion, right? Not anything else. Why is the cylinder proportional to the square of the span, right? Instead of okay, think about this airplane, right? This airplane. I mean, if you look at its wake, you can kind of see this cylinder getting disturbed and moving down. If there is actually a cloud behind it for you to visualize, but why is that the case? Only air, like if you think about the air close, that actually gets close to the airplane, only the projection of the plane is not a cylinder, right? It's much fatter. I mean, it's much flatter than a cylinder. So why it is that cylinder of air gets disturbed and not just the projection of the airplane that's very squashed vertically but very long horizontally? Why does the span matter but not the height of the airplane, right? So there is a lot of things you can ask about why that the model itself cannot answer. That is why in this course we are actually going, it's almost going down like the level of turtles. Have you heard of the kind of a story about a physicist kind of explaining how the universe works? And the old lady comes up and tell the physicist, that, okay, the world is actually sitting on the back of a turtle, right? And that's floating in a giant ocean. And the physicist asks, I mean, if that's your worldview, what is actually underneath that turtle? Like, what is carrying that turtle? And the old lady says, you don't understand. It's turtles all the way down. The turtle is sitting on the back of an even bigger turtle, who is sitting on an even bigger turtle, etc. I mean, aerodynamics is kind of like this. So here we are starting with a very high-level model, right? That's very easy to understand. Like you all derive the entire consequence of the model. The model is very easy to describe, just the cylinder of air. And the consequence of the model is also, it's a short kind of a mathematical procedure to derive the consequence of the model, right? Lift, induced drag. But as we see, it is not exactly satisfactory. So what we are going to be doing is we are going to be deriving like high-level models like this from more fundamental models, right? Like the most fundamental model is the first principle, like quantum mechanics, or things that we can no longer explain why. But we're not going to start there. We are going to start something called the Navier-Stokes equation. We're going to start from the conservation of mass, momentum, and energy. And we're not going to be asking, like, why is mass conserved? Like, why is momentum conserved? Why is energy conserved? And then we derive things from there. But we're not going to start with the Navier-Stokes equation, right? We're going to basically moving down the chain, starting from very simple models, easy to work with something slightly more difficult. So the chain of model is the following. It's not a chain. It doesn't like follow exactly as a chain of models, but we're going to be discussing incompressible potential flows. Okay, so and for each model, we are going to explain like in what scenario it is useful, like in what way it is wrong. For example, incompressible potential flows is going to be wrong once your flow is fast enough. Your flow no longer becomes incompressible. It is also wrong when the potential flow assumption becomes false. Potential flow assumes the whole flow is solely under the influence of pressure. Okay, pressure is the only thing that moves air through space. Okay, so when it is not true, well, it is not true when, for example, the air is affected by heating, right? Is affected by friction. So these are the scenarios where potential flow doesn't work anymore. So and then we're going to derive what's the consequence of potential flow. Like what can you say if these assumptions are true? And we're going to be looking at the lifting line theory, which you already studied in Unified, the vortex lattice method, and implicit airfoils. I mean, if you think about airfoils, we think about a lot. I mean, in aerospace engineering, we think a lot on airfoils. But an airfoil is a model. It assumes that you have a wing that's infinitely long and consists of exactly the same airfoil at any point in span, with exactly the same angle of attack, exactly the same chord length. Okay, only in that scenario, your conclusion of an airfoil is actually correct. But in realistic scenarios, you never have that case, right? So basically, you have to almost kind of use your experience to judge, okay, in what scenario I can consider the flow quasi two-dimensional flow over an airfoil. We'll study boundary layers. Okay, a lot of people think about boundary layer being like something physical, right? I mean, when you have a flow over a solid body, when you zoom in into the very close to the surface, you have boundary layers. But what we are talking about is boundary layer theory. So any boundary layer theory, flow separation, viscous drag, or anything, actually is based on an approximation. And this approximation says that the height of the boundary layer, the thickness of the boundary layer, is much, much smaller, is infinitesimal compared to any geometric features like the curvature of the wing, the size of the airplane, or the size of anything, right? Only under that kind of scenario would you be able to actually say anything concrete using anything we are going to be learning about boundary layers. So all of this has approximations, and one of the things people kind of struggle in aerodynamics is to make any statement on anything, it kind of requires you to have a non-theory based judgment on what model is applicable in this scenario, right? So we actually don't really have anything unless you go to a more complex model and use the more complex model to do some computation. And by the way, computation is one of the things we're going to be using a lot in this in aerodynamics. We're going to be using a lot of software. That once you go to more and more complex models, doing hand calculation is no longer feasible, and pretty much all of these models, except for the one we just went through, right, is too complicated in most practical scenarios to go through the calculation by hand. So what we're going to be learning is we're going to be learning application of these models in extremely simplified scenarios, so you can actually gain some intuition by hand calculation. Okay, but then for example, for the project, you probably won't be able to use any of this with hand calculation. You're going to be using software and programming. And finally, we'll go to compressible flows. We have shock expansion theory. We have a supersonic thin airfoil theory. And all of these models are based on Navier-Stokes equations. Okay, all of these models can be derived mathematically by making assumptions and approximations. And this class is actually not going to be about these derivations. And because if you read some of the Russian textbooks on fluid mechanics, it's just a huge book of very dense mathematics that derives things from the Navier-Stokes equations. And it's I would say beyond even the typical graduate level fluid mechanics course to actually do all of these derivations. So we are going to actually jump through a lot of the derivations and say, just trust me, if you do the math, you are going to get something like that. But we'll be focused on really the consequence of these theories and the models. Okay, so yeah, so this week is really kind of the introduction of all of this, and the next week we're going to start with the Navier-Stokes equations, and from there, because like in a lot of these theories, in order for me to not derive it, even to explain why this is true, we need the Navier-Stokes equations. And by the way, we're not going to start with this. This is actually from NASA's website. And it's a good reference, but it's the most useless thing for somebody who is first time learning aerodynamics. So we're going to start with extremely simplified scenario and start to build upon. Okay, if you now consider viscous, not just the pressure, you will have this additional term. If you now have compressibility, you will have this additional thing. So we'll start with something that doesn't have most of the stuff in here, and then we'll add more and more complexity as we learn more and more models. All right. Okay. So I'll see you in the wind tunnel tour today. So did all of you sign up for a time slot? Yes. Yes. Yeah. So if for somebody like either 1 or 2 doesn't work, I'd be happy to bring you to the tunnel like at some like other hours we can schedule. But like if all of you can fit into 1 or 2, it's perfect. All right. Okay. All right. I will.